Hi guys, so welcome to another video. In this video we're going to talk about another aspect of elementary number theory known as Euclid's algorithm. Euclid's algorithm is basically a way of finding the greatest common factor of two numbers in a pretty effective method. And this method, obviously we're going to look at how to do it, but most often it's actually programmed into computers to do over a long number of factors. And the reason why this is done is because it's more effective than just breaking down each number into its individual factors, than comparing every single factor and seeing which one is greater or smaller. Because obviously, if we have a number, for example, like 20, that's only going to take us a few seconds to break down into factors. But if we have numbers which are significantly larger than even 1,000, that might take us a while to break down into factors. And to find the greatest common factor between two integers, we have to do that for both of them. So that's going to take us even longer. So how can we make this more effective? Well, we're going to use something called Euclid's algorithm, which was a method essentially devised by Euclid on how to find the greatest common factor of two integers. So how do we do this? Let's say that we want to find the greatest common factor of 54 and 12. Okay? So in order to understand this visually, first we're going to draw out the 54 as kind of a long big block. Okay, so this is 54. Now how many times can 12 go into 54? Well, 54 itself is indirectly divisible by 12, but the closest multiple of 12 to 54 is 48, which is divisible by 12. So how can we express that? Well, let's say that we have a block which is a bit smaller. So it goes almost all the way. And it consists of 4 blocks of 12. Now my blocks aren't exactly the same size, but you get the point. Just assume that they're the same size. So this is 12, 12, 12, and 12. As I said before, 54 isn't exactly divisible by 12, so that must mean that we have a remainder when we divide. Now, what's 54 minus 48? That's 6. So we have a remainder of 6. We're just going to write that down over here. And now what Euclid's algorithm tells us to do is essentially to get down to the smallest building block, which can go into both numbers, right? Because that's the greatest common factor that we're trying to find. Or the first kind of number which can equally fit into both. Okay, let's take 6. Now, 48 is actually divisible by 6. So what's nice here is that our proof is complete a bit faster, so I'm going to use another more complicated example in a second. But just to illustrate the point with a simple example first. Okay, so we can see that 6 goes into this block, but since our remainder of division by 12 was 6, that must mean that we can actually add in the 6 that we need here. Therefore, what does that mean? That must mean that the greatest common factor of both of these numbers must be 6. Because let's see what we did here. Essentially, we divided 54 by the other number that we were trying to find the greatest common factor of. We saw that they don't equally divide each other, however, there's a remainder. So what are we going to do with that remainder? We're going to see how many times the remainder itself, which is, you can kind of think of the next smallest block that we can put into 54. So the first block that we put in is 12, it doesn't go in equally, and what we're trying to find is we're trying to find blocks that are going to evenly go into both 12 and 54. And we got lucky. I didn't choose these two numbers to be easy on purpose, but as you can see, they actually have a greatest common factor which is quite easy to find, which is 6. And the reason why that works is because the 6 obviously goes into 12 and it goes into 54. And this is the first number that we found which evenly goes into both. Okay, So let's try this with a more complicated example because I feel like this doesn't really illustrate the power of Euclid's algorithm that well. And also, side note here is obviously if you're trying to find the greatest common factor of a number and a prime, then the greatest common factor will be 1 because no prime is divisible by anything except itself in 1. So don't bother applying this algorithm with a number that you definitely know is prime because that's just a waste of time. And we call numbers whose greatest common factor to be 1 as coprime, that those two numbers don't necessarily have to both be prime. So to clarify that, for example, what's a good example? If we take 4 and 9, the factors of 4 are 1, 2, and 4. The factors of 9 are 1, 3, and 9. Now, obviously, 4 and 9 are not the same number, 2 and 3 are also not the same number, so the greatest common factor is 1. Now, neither 4 nor 9 are prime numbers. However, just because of the fact that the greatest common factor is 1, we call them coprime. That's kind of just a side note. Okay, so we use 12 and 54. Let's use some more difficult numbers. Let's take let's just take 12 and 8. Okay, so we're going to repeat the same process. We have this big building block of 12. Now how many times does 8 go into 12? Clearly 8 goes into 12 only once. And we have a remainder of 4. I'm going to show that by a dotted line. Okay, so how many times does 4 go into 8? 4 goes into it twice. So the remainder when you divide 8 by 4 is 0. Therefore, that must mean that we can actually apply this all the way. Therefore, the GCF is 4. So I actually accidentally picked another pair of simple numbers. So let's try to take some more difficult numbers. And yeah, an important point here to realize is once you get to a point where as you're dividing the block by the remainder, you get a remainder of 0, that must mean that the process is complete. Because as you can see here, that must mean that we can essentially put whatever remainder we want into the original number an even number of times. So we're going to have integral blocks, or an integral number of blocks. Okay, so the two numbers that we're going to try and look at are going to be 49 and 8. And let's see what we get. So first we draw out our big block of 49. Okay, we know that 49 is not evenly divisible by 8. However, we know that 48 is divisible by 8, so we're quite close. And note that this sliver, which represents 48, is a little bit smaller, right? Okay, and we know that 48 is equal to 6 times 8, so we're going to have 6 blocks of 8 go into this. And we have a remainder of 1. Actually, this is interesting because what this tells us is that once we take blocks of 1, obviously every number is divisible by 1, as long as we're talking about integers. So if we take 48 and divided by 1, we're going to have 48 groups of 1. And I'm not going to draw that out, but basically we're going to have lots of these little groups. Now this is not an exact number, but just to kind of represent the fact that we're going to have lots of groups of 1s that are going to be evenly going into 48, and they can also replace this little remainder here. So that must mean that they also go into 49 and into our divisor, which we're trying to find the greatest common factor of 49, right? So what does this mean? We got to a part with the remainder of 0 when we divided by the remainder of 1. So when we divided 8 by 1, we got a remainder of 0, and when we divided 49 by 1, we also got a remainder of 0. So that must mean that this remainder of 1 equally goes into 8 and 49. Now why is this interesting? This tells us that the greatest common factor of 49 and 8 must be 1. So going back to what I just said previously, that must imply that 49 and 8 are coprime. So just to summarize kind of what's the main idea here, essentially as we're using Euclid's algorithm, we're trying to get down to a number which is going to evenly divide both the larger number out of the two and the smaller one. And as soon as we find one which evenly divides both of them, that must mean that we get a remainder of 0 looking at both of them, right? So that implies that the first number which gives us a remainder of 0 must be the greatest common factor. So I hope that this visual explanation kind of makes sense of the Euclidean algorithm and where it comes from, because I do remember the first time that I learned this, it actually didn't make any sense to me. And even though I could apply it mechanically, I didn't really understand it. But I feel like seeing this visual proof kind of helps clarify it. Thanks for watching.